And today we are going to discuss the blood flow dynamics and how blood flows in a vessel, what are the laws, how do we measure the blood velocity, a measurement of blood velocity we'll discuss about how that tomography is done and all. Laminar blood flow, what is laminar blood flow, how we define the Reynolds number, what is the Poiseuille-Huygens formula and all, and shear stress, about shear stress a bit. So basically, we are discussing hemodynamics only, but I will take it at a bit higher level. And the primary thing that I'll be teaching is Ganong. You can find all these things in Ganong. You can just give it a read after I have taught this. And this is important in your CVS point of view. So let's start. So we know in a vessel, the blood flows as water also flows and air also flows in such a manner because blood is a fluid, right? So blood flows from a region of high pressure to a region of low pressure. So from high pressure to low pressure, the blood flows. Okay. And how do we calculate the flow? The calculation of flow is dependent upon the pressure gradient as well as the resistance suffered by the vessel. Okay. So flow is calculated by delta P by R. So basically today's class is all about physics. If you're good in physics, you will enjoy the class. And if you're not, then you should be able to bear the class. Okay. I'll make it bearable, no problem. Flow is delta P by R, that is your pressure by resistance. Okay. And here the pressure means the effective perfusion pressure, not the absolute pressure. It is the effective perfusion pressure. Okay. What do you mean by that? Let me discuss. If this is a blood vessel, let's say the pressure is P1 here and P2 here. If the blood will only flow from P1 to P2, if P1 is greater than P2, right? And this effective perfusion pressure delta P is P1 minus P2. Was P1 minus P2. And this P1, remember, it is the intraluminal pressure on arterial end, and P2 is the intraluminal pressure at the venous end. So each capillary has an arterial end as well as a venous end. Let me tell you. So blood flows from the arterial end to venous end. This P1 will be the uh, intraluminal mean intraluminal pressure at arterial end. And same with P2, it is the mean intraluminal pressure at venous end, at the venous end. Understood? So let's move ahead. Okay. Uh, After this, we want to discuss some uh, concepts like R unit. You should know about R unit, although it is not directly asked. What is R unit? If the mean arterial pressure, just mark my words, if the mean arterial pressure, you can say aortic pressure, okay. If the mean aortic pressure, let's say it's assuming it 90 mmHg, and the left ventricular output is also 90 ml of liter, 90 ml per liter, then the flow is given by R unit. So R unit is defined as when mean aortic pressure is 90 mmHg, and the left ventricular output is 90 ml per liter, then this flow F is equal to 90 by 90, right? Equal to 1. And this flow in this case is known as 1 R unit. 1 R unit. As in physics, you describe the standard units. Likewise, we describe the R unit in the terms of your mean aortic pressure. We take the help of this mean aortic pressure and the left ventricular output in order to take out the R unit. Okay. After this, we'll discuss about the blood velocity measurement. Blood velocity that is a flow measurement. How do you measure the blood velocity? These are not your core concepts of physiology, but these are some of the advanced concepts that I am taking. If you're interested in USMLE and all other exams, then it will be very, very helpful. In NEET PG also, one or two questions may come, although it is out of scope of our curriculum. Okay, and yeah, we're in blood velocity measurement. Basically, what we do whenever we want to measure velocity, we take the help of Doppler. Doppler effect we all know from physics. So this blood velocity is measured by Doppler flow methods only. Doppler. Let's assume if this is a blood vessel. Let me draw a blood vessel. Let's assume this is a blood vessel. Then we irradiate an ultrasonic wave, and this ultrasonic wave will be reflected back into a sensor, downstream sensor. So if some rays are irradiated, that is your UV rays, this will be reflected back, and there will be a sensor here. This is known as your sensor. Okay, and the sensor will sense the waves. This is a direct method. This is the direct method which is done by Doppler flow methods. Okay, and some other methods are there for measurement of blood flow velocity, which are called as the indirect methods. Indirect methods, like first of all, we have your Ketty and Tuo method. Some indirect methods are there also. These all are given in your Ganong textbook. Probably not in Guyton. Guyton doesn't cover this all. Yeah, some parts of laminar blood flow and Poiseuille equation, Reynolds number, these are given. But this measurement parts and experimental physiology parts are probably skipped in Guyton, as per my knowledge. Although you can check. Okay. So indirect methods, first we have Ketty's N2O method. Ketty's N2O method. In this Ketty's N2O method, we basically are what we are doing is this nitrogen dioxide is basically used in measurement of blood flow by injecting, and all things are there, like the whole procedure is there, but the whole procedure is not needed. But just a MCQ fact to remember is that this method is used for measuring the cerebral blood flow, for measuring cerebral blood flow, for measurement of cerebral blood flow. Okay, and then we have another method, that is power clearance. Probably you might have read the PA clearance in your renal physiology chapter, that is your para-aminohippuric acid. Okay, this PA is your para-aminohippuric acid, and this PA clearance is the distance that is traveled, the clearance capacity. Now, the clearance is measured by UV by P. You know the formula. If the creatine is there, we use UC and B in PC. Okay, this is all our clearance, and many equations are there in urine clearance, creatine clearance, etc. in renal physiology. Here we do PA clearance, that is the para-aminohippuric acid clearance, and this is, of course, you can know this is used for measuring your renal blood flow. Okay, renal blood flow, RBF, and we also use a venous occlusion plethysmography. Venous occlusion plethysmography, although it is beyond our syllabus. Venous occlusion plethysmography. Or I doubt, probably my spelling is a bit wrong. Plethysmo, plethysmo. Probably it is plethysmo. Yeah, it is plethysmography. And if it's still wrong, then just don't mind. Okay. So it is a method used to measure the blood flow in extremities, in your hands and legs. It is for measuring the blood flow in extremities. So just you have to extremities. What is that? Yeah. So that is about the venous occlusion plethysmography. Okay. And this is used for measuring the blood flow in extremities. Yeah. So we're done with the blood velocity measurement and the blood flow measurement. Now let's come to the laminar blood flow. Laminar flow. You should have a basic idea about laminar flow because blood flow occurs up to a particular critical velocity. If blood flow exceeds that critical velocity, that is a VC, then it is called as a turbulent flow of blood. And this critical velocity, this probability of turbulence, is given by the Reynolds number. Okay, how much the blood is turbulent is given by the Reynolds number. You know all this from your physics. Like if Reynolds number increases, we say that the probability of the blood to become turbulent increases. So laminar flow is basically when blood flow in straight layers which are parallel to each other. Okay, straight layers which are parallel to each other, and this distribution of velocities is known as a parabolic distribution. So whatever I told, let me just represent here. Let's say laminar flow. If you want to understand the laminar flow, this is a blood vessel. This is a blood vessel. Okay. So basically, what I'm saying is in a laminar flow, the blood flows in this parallel fashion, a particular parallel fashion. This is the fashion in which the blood is flowing. And this you can say is the shape of a parabola. Is a parabolic distribution of velocities. Is a parabolic distribution of velocities. Okay. And as you move up, the velocity will decrease. V decreases. As you move down, also velocity is decrease, and in the middle portion, the velocity is higher. This is known as laminar blood flow. And this laminar flow, just note this very carefully. I'm running out of colors. This laminar flow occurs up to a particular velocity only. And this particular velocity, mark my words, this particular velocity is known as VC, not VO, VC, that is a critical velocity. That is a critical velocity. And this critical velocity is given by a number that is called the Reynolds number. Okay, we'll discuss what is the critical velocity and how will we do. Yeah, so basically, if we move above critical velocity, if more than VC, then the blood flow is known as a turbulent flow. Turbulent flow of blood. The blood flows in this fashion. And this is a blood vessel, and the flow of blood will be like this, turbulently. You must have heard about the Brownian motion, like that. Just we don't use the term Brownian motion in case of this blood and all. Okay. And this probability of turbulence, this probability of turbulence is given by the number which is called the Reynolds number. This probability of turbulence is given by the Reynolds number. Reynolds number. That is represented by RE. Understood? So basically, we saw how the blood is basically being turbulent, and if the critical velocity is exceeded, we'll know how if Reynolds number lies between that. If it increases beyond 3000, I will say, then there will be turbulence, because about 2000 to 3000 we will get the laminar flow of blood. Okay, you can just write 2000, the Reynolds number 2000 to 3000 according to Ganon, of course. Other books, some say other values, some say 1000 also. This 2000 to 3000 Reynolds number will give us a laminar flow. Just don't forget this range, because the ranges and the data given in Ganong is very standard. It is meant to be, it is just, if there is a controversy in any question, then the data given in Ganong will be deemed correct. Okay. And Reynolds number is calculated. There's a formula for Reynolds number. You might have known this formula from your physics basic. This RE means your Reynolds number, that is your rho VD by nu. RE is rho VD by nu. This is the formula. Okay. And if you want to know this, this is a Reynolds number. This what is the rho? Rho, you know, density. Density. But the V here is just, I put a dot because it is the average velocity of flow. Velocity of flow. It is the flow velocity, so it must be at the average velocity. And this D is the diameter of tube or your blood vessel diameter. You know very well about nu. Nu is the viscosity of blood. Viscosity of blood. So this is the Reynolds number. This is the formula for calculating the Reynolds number. And if there is increase in Reynolds number, if this Reynolds number increases, then your turbulency also increases. Understood? And this RE increases, your turbulency also increases. Yeah. So basically, if there is a constriction of an artery, if there is vasoconstriction, let's say, if an artery is there, right, like this, and if it gets constricted to form this, it is vasoconstriction. So if there is vasoconstriction, then the velocity will increase. This V dot will increase, and if this V dot will increase, the Reynolds number will increase. It will produce the turbulence, and Reynolds number increase means there is increased probability of turbulence. So vasoconstriction will produce turbulence. This is very important as the pathology point of view, because the formation of the blood clot, the thrombus, the emboli are dependent upon this turbulence only. Okay, this is one of the factor. Yeah. And yeah, another thing, what is the clinical significance of these things which I'm telling? That vasoconstriction will produce this turbulence. RE increases means turbulency. What is the clinical significance? So let's say a patient comes to you and you have to measure his blood pressure. This is the patient. You tie the BP cuff here. Let's say you tied the BP cuff. So what the BP cuff does, this BP cuff will constrict the arteries, will cause vasoconstriction. This vasoconstriction will increase the V dot, increase the Reynolds number, increase the turbulency, and this increase in turbulency in blood vessels will produce some sounds which are known as throat cough sounds. Throat cough sounds. And this throat cough sounds are important because this give us an indication of your systolic blood pressure as well as your diastolic blood pressure. The moment where sound appears is the systolic, like when it disappears, when you increase the pressure, and when it reappears again, it is the diastolic, of course. Okay, so basically, this is the point where the throat cough sounds appear. So, clinical indication of this vasoconstriction due to increased turbulency or increased turbulence due to vasoconstriction is your throat cough sounds. Okay. Okay. Now we'll discuss about one more advanced concept, that is how is shear stress cause gene activation. So basically, this is not much well dealt with, but you know about shear stress. A shear stress is just Y. Okay, a Y, it is represented by Y. You must have known from physics. If this is a blood vessel, and if you give a force, that's can relate with physics. This was a block lying on the ground. You must have drawn free body diagrams and all. Okay. This is the force which is given like this, due to which it gets distorted. Okay, this is the shear stress, and this shear stress, if this shear stress is applied in this format, the blood vessel also acts in the same manner. Okay, this is the y, which is the shear stress, and this shear stress is proportional to your viscosity into your dy by dx. What is your dy by dx? The velocity gradient. What is the dy by dx? The velocity gradient. Okay. So this is the shear stress. Dx you can say, or you can just well say it dr, because it is the rate. Okay, dr. Yeah, and this is the shear stress. Okay, and this is the velocity gradient, delta v. I'm writing delta v for the velocity gradient to well understand. Okay, so this shear stress will change the expression of genes. Will what will this shear stress do? This shear stress will basically, it will do three things. It will stimulate the growth factors, not girlfriends, growth factors. Okay, it will stimulate the integrins, and it will stimulate the related molecules, some related molecules, miscellaneous, I can write. Okay, and let's discuss about what it can do. This shear stress can activate many genes. Of course, you can write the name of some genes which are activated by shear stress. Like, what are the things that are activated by the shear stress? The shear stress activates NK K beta, natural killer cell K beta. Okay, it activates the AP1 gene. AP1 gene, and this NK K beta is basically stimulating the formation of VCAM1. This is not much important. SSRE, okay, and EGR1 gene. Many are there. Okay, these are some of the genes which are activated by shear stress. So basically, this is one of the concepts which are not much needed, just to know the genes and what is happening basically in this formula, of course. Okay, yeah. So this is the thing, and let's move on to another concept which is there in our Guyton and as well as Ganong. This is the average velocity. Average velocity. So what is average velocity? Average velocity is represented by v dot, and this v dot equal to q by a. What is q? Q is your, what is q? Q is a flow. Okay. So if q is a flow, if this q is constant, if this flow is constant, and a is the area, of course. If this flow is constant, then v and a is inversely proportional, right? If area is increased, your v will decrease, and if v will increase, your area will decrease. Yeah. So average velocity, the order will be average velocity. This is the order: aorta, maximum average velocity, then smaller vessels, then your capillaries. Right? Understood? Yeah. Okay. In Genong, there is a thing given which is called as the arm to tongue circulation time. Another thing, just I want to discuss with you, is your arm to tongue. Arm to tongue circulation time. What is this arm to tongue circulation time? Is that, first of all, you will give a to a vein, okay, to a arm vein, your cephalic vein, basilic vein, or median cubital vein, anyone can give. So there is an injection of a bile salt to an arm vein. Okay, this median cubital vein is chosen. Injection of a bile salt, remember. So we'll inject a bile salt into arm vein. We injected a bile salt into arm vein, and after the first appearance of bitter taste, let's say this is the time T1. At the time T1, you injected a bile salt into the arm vein, and after this time T2, the first appearance of bitter taste, will be marked as T2. T2. So T2 minus T1, that is first appearance of bitter taste injection to this first appearance bitter taste. That means what are you doing? You are basically calculating from the arm to tongue. The bile salt is basically traveling. So we're basically calculating the time. Okay. And this T2 minus T1 is called as the arm to tongue circulation time. Okay. And this is normally 15 seconds. Look how fast. Okay. This is our power of our body. Okay. In 15 seconds, it gets like bitter taste. Okay. And yeah, then we'll discuss in your hemodynamics, that is the Poiseuille-Huygens formula. Equation. Poiseuille-Huygens equation. Yeah. So let's discuss the Poiseuille-Huygens equation. Okay. So you must have heard about the Poiseuille's equation. You must have heard about the formula that is given. That is 8 nu L by your pi r to the power 4. That is your r is proportional to the radius to the power 4 and all. Okay. We'll come to it. And this Poiseuille-Huygens formula is basically what it is basically. Okay. It gives a relation. Okay. It gives a relation between the flow. Okay, three things are there between the flow, the velocity, as well as the radius of the tube. Three things, three variables are there. It is a relation. If you want to define it, you can do it in this way. Relation between the flow, the velocity, and the radius of the tube. It is basically a relation, okay, between the flow, the velocity, as well as the radius of the tube. Okay. Uh, what is the formula? Let me tell you. This flow is, what is the flow? Flow is given by your pressure gradient. What is this pressure gradient? With PA minus PB. Must have heard this formula, about this formula in physics only. Right. PA minus PB. So this is the pressure gradient multiplied by a constant that is pi by 8. Pi by 8 is a constant one, multiplied by 1 by nu. 1 by nu is a 1 upon your viscosity. Okay. And r to the power 4 by L. What is L? L is the length of the tube. What is R? R is the radius of the tube. Yeah. Okay. Yeah. So this is the flow. This is the flow. We'll derive the formula like this. You must have like seeing that we'll basically discussing physics only. Okay. So it doesn't matter. This physics will like be helpful in your medical curriculum also. You might have not thought in your pre-med times, but it is a very crucial subject. Okay. Yeah. So flow is given by your pressure by resistance. This formula you know. This formula you know. So this R will be given by this R. This R will be given by pressure by flow. Right. So press del P, that means PA minus PB. And this whole thing in the place of flow, I will substitute. Okay. I will substitute this whole thing, that is your PA minus PB multiplied by pi by 8 multiplied by your 1 by nu multiplied by your What was that? R to the power 4 by L. Yeah. Cancel. This R will be 8 nu L. Just brought it up by pi R to the power 4. 8 nu L by pi R to the power 4. This is the formula. Okay. And here the R is R to the power. This is the Poisson equation, which is there in your. This part is important. Some numericals are often asked in your MCQ exams based upon this relation only. Okay, I just derived the formula, so just to give you an idea of how it is happening and all. Okay, there is an effect. I don't know if it is needed for you or not. It is known as a Farias. Okay, Lindquist effect. Okay, it's difficult to pronounce. I know. Farias Lindquist effect. Fair Okay, you can just pronounce it like Fair and Lindquist effect. We'll discuss what it is all about. So, what is this Farias Lindquist effect? Uh, this is responsible. This effect is the main culprit. I don't say culprit, but it is responsible for the difference in nature of flow along the small blood vessels. What happens is that in a small blood vessel, if we are taking a small blood vessel, assume this is a small blood vessel. Assume this is a small blood vessel. So the small blood vessel, in a small blood vessel, there is movement of this RBCs to the center of the tube rather than to the periphery. Okay. So basically what happens is all the RBCs are coming to the center of the tube. And the plasma is localized to the wall. Here in the center you have RBCs and plasma at periphery. The plasma is at periphery. So the net change in viscosity per unit change in hematocrit is smaller in body as compared to in vitro. Okay. So basically this is happening. This is just an effect. You just don't need to like basically it's a viscosity related effect. Like in clinical settings also viscosity is evident. Like you know about the plasma proteins. If there is increased plasma proteins, there will be increased viscosity. Right. If there is abnormally rigid RBCs, there will be increased viscosity. If the RBCs are rigid, okay, rigid RBCs, for example, in hereditary spherocytosis, you know about the hereditary spherocytosis, the ankyrin, the spectrin, and all. Okay, in hereditary spherocytosis, HS I'm writing. So there is increased viscosity. So viscosity is a clinically significant parameter. In your clinical settings also, you must have an idea of this also. Okay. So this is about your Ferris Lindquist effect. What is happening, I just told, and you just don't need to go into more detailing because it's of course beyond the scope. This effect is also is not in your Guyton, this is given in Ganong, so I covered it. Okay. Yeah. So in hemodynamics, in your Ganong textbook, sorry, in your Guyton textbook, there is a topic given that is the presence of blood in various parts. Okay. Uh, the proportion of blood varies in various parts of body. This is if you want to know, then 84%, just know 84% is in systemic circulation. You know about the systemic and pulmonary circulation, I believe. Systemic circulation is the blood is circulating throughout the body, and pulmonary is when it is going to the lungs to get oxygenated and coming back here to the heart. Okay, so in systemic circulation, there's 84% of blood, and this 84% is also divided in three parts. The proportions I'm writing 64%, 13%, and 7%. Can you just guess 64% blood will be present in which part? Which vessel of our body is known as your you can say a reservoir of blood, vein or artery? Vein. Okay. So this is veins. 13% is present in your arteries and 7% in your capillaries. So 84% blood, 64% in veins, 13% in arteries, and 7% in your systemic arteries and capillaries. Just you can remember capillaries. Okay. Even the heart, of course, 84% is done. So of 100%, we are remained with some, not 26, 16%, right? 16% is left to be known. Okay. Of this 16% blood, 7% is in your heart. 7% blood is in your heart. I'm just drawing this heart. Okay. 7% is in your heart, and about 9% is in your pulmonary vessels. So this point is covered in your hemodynamics. That's why I told you. Okay. Yeah. Another important concept we know, we'll read, that is a peripheral resistance. Peripheral resistance. So let's learn about the peripheral resistance. What is peripheral resistance? This is represented by PR. So it is an impediment to the blood flow. So basically, if the blood is flowing, then we are giving a barrier. We are giving a push to stop the blood flow in the opposite direction. So it is an impediment to the blood flow, and this peripheral resistance is measured in peripheral resistance unit. Okay, PRU. It is called PRU, which is measured in PRU. So what is PRU? Yeah, let's understand what is PRU. We'll understand easily. Let's say this is a blood vessel. Okay, if the change in pressure, the delta P, that is a pressure gradient, is 1 mmHg, the pressure gradient is 1 mmHg. If the blood flow, if the flow is 1 ml, blood flow is 1 ml per second. Okay, mark the units, very important. 1 ml per second, let. Okay, then the resistance, the R, which is given by the F by delta P. Okay, just a minute. Yeah, so we're back. There's some glitches. Yeah. Okay. So this resistance, which is given by, sorry, I wrote R by delta P. This is delta P by R, delta P by F. Okay. Yeah. It will be known as, this resistance will be known as 1 PRU. So 1 PRU is the resistance offered by the flow of blood when the blood is flowing at a rate of 1 ml per second in the pressure gradient 1 mmHg of pressure. Okay, ignore the background noises. Okay, and yeah, this PRU is different in systemic as well as in pulmonary circulation. Which circulation do you think will be having more resistance? If the blood is going to just the lungs or whole body? Whole body. So this systemic circulation will be having 1 PRU, and this pulmonary circulation will be having about 0.13 to 14. It's right. 0.14, I have, 0.14 PRU. Okay, and so this is the impediment, and this PRU is the unit of peripheral resistance. Okay, about the implications of peripheral resistance, which is a separate chapter. We just needed to discuss this much of peripheral resistance in the hemodynamics topic, because I'm covering the hemodynamics only. Okay, yeah. When I told about resistance, did I mention conductance? You know the formula. Okay, conductance C is 1 by resistance. You know this. Just not much this thing is needed. Okay. Okay. Another thing. There is a law called as the fourth power law. And just you can see the formula above. Okay, just a minute. Yeah. Okay. Look at this. So we know this relation is there. The resistance, this is the R, not the rate. Just remember, this is resistance, okay? This resistance is inversely proportional to the R to the power 4, to R to the power 4 radius, or you can write diameter to the power 4. Proportional. Radius, diameter doesn't matter. So if this is a resistance, what will be the flow? Flow is inversely proportional to R. Flow or rate, you can say, is inversely proportional to R. And if this flow is inversely proportional to R and this R is inversely proportional to R to the power 4, small r to the power 4, then the flow is directly proportional to the small r to the power 4, right? So here we can write fourth power law is that the rate, remember not resistance, rate. Resistance will be inversely. Rate is directly proportional to R to the power 4, where R is the radius, or you can write diameter also. Radius, and basically diameter is written in books, diameter of blood vessels. Not equal to, it is proportional. So radius, diameter doesn't matter here. So if someone says that the diameter, like if blood vessel is there is vasoconstriction. Okay. If this was 2, okay. If it just don't, if it is x, let's say it is x, there is vasoconstriction, it becomes x by 2. So how much will be rate? Will be there. Okay. So x is reducing to x by 2. So rate will reduce by this r to the power 4 means r by 8. Sorry, 2 to the power 4 is 416. Yes. So rate will be reduced by 16 times. Yeah. So these numericals are often asked in these parts. Yeah. Last but not the least, yeah, two more things we have. One is your vascular distensibility. Another thing is your vascular distensibility. Vascular distensibility, and another thing is called as a vascular compliance. Your vascular compliance. So vascular distensibility is the range, is the okay. Vascular distensibility. Vascular means blood vessel, related to blood vessel, and distensibility means how much you can distend, the ability to get distended. So how much you can distend a blood vessel is basically its vascular distensibility of the blood vessel. Okay, and this vascular distensibility, the most distensible vessel. What is the most distensible vessel? Okay, do you know? Veins. Veins are the most distensible. Yeah, it is given by a formula. You don't need to remember the formula. It is given in your guidance. Increase in volume. It is given by increase in volume by increase in pressure. Increase in volume by increase in pressure into its original volume. Okay, by its original volume. Understood? Understood? Yeah. You can basically represent in a numerical format, as we are the students of science and we love physics. Increase in volume is delta V, increase in pressure is delta P, and its original volume is VO, original volume, VO. And this is VD, that is a vascular distensibility. Let's talk about VC, that is a vascular compliance. So vascular compliance is the amount of blood, just mark my words very carefully. Total blood or amount of blood, whatever you can say, that can be stored. Okay, the total blood that can be stored in a given part of a circulation, just any blood vessel you can take, a given part of circulation for each of pressure increase. You increase the pressure and you're storing the blood in a particular part. And how much blood you can store in the particular part per increase in pressure is given by vascular compliance. Okay. So vascular compliance, just if you didn't understand the definition, doesn't make you can just read your guidance textbook or your Ganong. In Ganong also, I hope it is given. Okay, I'm not sure. Okay, vascular compliance, and how it is given? It is given by increase in volume by increase in pressure. That is your del V by del P. That is your del V by del P. Okay. So vascular distensibility is basically vascular compliance. You can see here del P by del P into your given by your original volume. This is a relation which is asked in some MCQ exams. Pre-test physiology and all, you can get this type of questions. Of course, it is not much more like important like this. Okay, and just a fact, if you want to know the compliance, that is a vascular compliance only. Okay, of veins is 24 times the compliance of arteries. The compliance of veins, just a minute. Probably the hand recognition is not working well. Okay, no problem. We are just to the end of the lecture. So compliance of veins is 24 times the compliance of arteries. This is the fact which is important, or you can remember. Okay. So that was about about your hemodynamics. You people told that you have doubts in CVS. So I just tried covering the CVS in some short videos. And this videos, if you have been listening me from the last 46 minutes, then will benefit from this. We covered the whole Guyton as well as Ganong. Basically, we covered the Ganong because hemodynamics is very well given in Ganong textbook. I love the part of hemodynamics in that textbook. Okay, so that's all in today's video. If you like the lecture, do give it a try. Do watch the video up to the end. Of course, as we are here, so I believe that you have watched the whole lecture without skipping any part. That's all. And if you want to reach out to me, you can just reach out to me at this is my Instagram ID if you want to ask some doubts, and of course your email is there. This is my email, so you can text me any of the doubts you want to discuss with me of any subject. And that's all in today's lecture. That's all. Hope you liked the lecture. Thank you and have a great day ahead. Bye bye.